Welcome back to Elements of Chemistry. Today we're going to continue our discussion of nuclear processes and we're going to talk about half-life. In terms of nuclear, half-life is the time it takes for half of a radioactive nuclei to decay into a new nuclei, parents to decay into daughters. Remember, you cannot predict when any one nuclei will decay, but in a sample of nuclei, 50% will decay into the daughter every half-life. This is a statistical measure, and we can't say exactly when any one nuclei will do, just that the sample will go down by approximately half. It's like when you flip a coin. You got a 50% chance of getting heads. Half-life is also used a lot in terms of chemical reactions, and you'll get more of that in kinetics. Half-life is how we look at medication in the body. When is it half strength? When is it going to leave? When has a toxin you've ingested worked its way out? So half-life is a measure of how long something takes to transpose or leave. So let's look at this. The half-life is going to give you an exponential decay graph. And remember, it's a probability. Approximately half is going to be gone every half-life. And just as an example, here's a few samples here. Polonium-214 has a half-life of 163.7 microseconds. There are some that are much shorter. Whereas the other isotope, polonium-218, is around for 3 minutes. Some isotopes like uranium are around for a long time. Here, 4.46 times 10 to the 9th years. You may have heard of carbon-14. Carbon-14 has a half-life of 5,730 years. We use carbon-14 for dating fossils and anything that was once a living material, because you have in your body naturally occurring radioactive carbon-14. If you eat food, you are ingesting some radioactive carbon-14 as part of your natural background radiation. And when you die, you stop eating, and this amount is fixed in your body. So if we look at the ratio of how much carbon-14 is there compared to carbon-12, we can figure out when you died. So we're going to use two methods to do this. The charting method, which is obviously the easiest, and then there's the kinetics integrated rate law method that you're going to use more in AP and pre-AP. So the chart method, let's look at an example. How many grams of polonium-218 will remain in a 100-gram sample after 15 days? I had a little typo there to fix it. So in the charting method, you set up basically a half-life, time, parent, daughter, and total. Your half-life, you're going to add 1 going down the chart. You always start at 0. And you can just go ahead and put in your numbers. 1, 2, 3, 4, 5, depending on how many half-lives you need. Now we're doing polonium-213 or 218. So at time 0 is 0. We're going to have 1 half-life. It's every 3 days. So 3, 6, 9, 12, 15. I get to stop here because we're looking for 15 days. Okay, our parent started at 100 grams. We had no daughter. Our total of these two has to be 100. So 1 half-life, we're at 50 grams of our parent, and we have 50 grams of our daughter for a total of 100 grams. Remember, law of conservation of mass still holds. The parent's going to go down by 2, so I'm going to divide 50 by 2 to get 25. I'm going to add that the parent lost, it lost 25 grams, to the daughter, so this is 75 grams, and our total has to remain 100. Some students find it easier to know that it has to stay 100 and subtract the parent. That tells you how much is daughter. Now, half of 25 is 12.5. It has to be 100 total, so that tells me this is going to be 87.5 grams. Half of 12.5 is 6.25. Has to be 100 for the total, so this here is 93.75. Half of 6.25 is 3.125. The total has to be 100, so this comes out to be 96.875. So how many grams remain after 15 days? Here's my 15 days. How many grams remains? Was that 3.125? Now, sig figs do matter. We had 100 grams here, so we're going to say 3 grams remain. Because of sig figs, the charting method is kind of the easy. way out. Okay, let's try another one. Let's determine the half-life of a radioactive isotope that decays to 3.1% of its original value in 4,500 years. You start with 100 kilograms. How many? So we want to get the half-life, and then we want to figure out how many grams of daughter. So there's really two questions in this one. So if we make a chart, we'll do it a little bit faster. So we need to do a half-life, time, parent, daughter, and total. Remember, we start at 0. We're going in percent, so we have 100% of my parent, we have no daughter, and we have 100% total. One half-life, we don't know how long that is. We have 50% of my parent, 50% of the daughter, for 100% total. Two half-lives, we don't know what that is. 25% of my parent, 75% of the daughter, 100% total. Three half-lives, we don't know what this is. We're at 12.5, can't write a 5 here, percent. So now we are at 87.5% for 100% total. Some of you may have already noticed this is kind of mirroring the one we did before, because in this first problem, we had 100 grams. We could have even said that's percent. So we can actually use that to help get our numbers. Because our percent's always one. Okay, now here we're at 5 half-lives. In this one, we're going to be at the 3.125%. So this is where we're at. And we have 96.875% of the daughter produced for my 100. And this occurred at 4,500 years. Okay. It took 5 half-lives to get to 4,500 years. We can take that 4,500 years, divide it by 5. That's going to give me 900 years. Let's check and see if that works. So if this was at 900 years, this would be at 1,800 years. 3 times 900, 2,700 years. 3,600 years. And yes, we come out at 4,500 years. We have 3.125%. A half-life is 900 years. So our half-life was 900 years. And how much of the daughter has been produced? 96, we'll call it 97% is now the daughter. Now you could have guessed that if it decayed to 3%, it's got to be 90% because the two totals have to add up to 100. So even if you didn't have time to do all of this process, you could have just looked and went, oh, I got 3% of the parent, means it's got to be 97% daughter. So charting method, smart way to approach a lot of these problems, especially multiple choice problems where you can break it down to a range. The kinetics method is a little more intense. So if you're in an academic level class, or this is all your teacher's asking, you can go ahead and go straight to the questions. But if you're looking at AP and looking at kinetics, let's know that kinetics, decay is going to be a first order kinetic process. So it's going to follow the first order rate equation. The natural log of x0 over xt equals kt. X0 is the initial amount, xt is the amount remaining, k is your rate constant. And you can find that rate constant from the half-life of a first order process. K equals 0.693 over T1 half. T1 half is the half-life. So let's look through this example. We have a piece of cypress wood from an ancient tomb, and it has carbon-14 to carbon-12 ratio of 79.5%, that of living cypress today. We want to find the time the tree was cut down to make the tomb. We can't tell exactly when the tomb was made, just when the tree was cut down. Hopefully those two would be within the margin of error. So let's look at what we know. We know the half-life for carbon-14 is 5,700. I think I put 20 here. Really, 30. Sorry, that's a 30. No, it is a 20. I think I had it wrong up above. Hey, did I? I did. Let's go back and fix that. So fix that in your notes. Maybe something didn't look right here. Okay, so if it's 5,720 years is my half-life, and we plug that into our K equation, K equals 0.693 over T1 half, so 0.693 over 5,720, that's going to give me a rate constant, K, of 1.21 times 10 to the minus fourth years. Okay, our original value, our x0 is going to be 100%. The amount remaining is 79.5. That's going to equal K, so our 1.1 times 10 to the minus 4 years over time t. We go ahead and solve this natural log. That's going to give me 0.223. I have my K, I have my T. Solving for T, that gives me 1,890 years ago. So the tree was felled 1,890 years ago. So if we take today's date, this video was made in 2025, and subtract the 1890, this tree was felled in 135 ACE. If you are in a CAP or pre-AP level class, this could be expected. If you are in an academic level class, on level class, I think that this probably would not be the method you would use. Okay, so let's go ahead and your turn. You can go ahead and pause the video and try these. So we're going to give ourselves a minute. Go ahead and pause, try these, and then come back when you're ready to check your work. Okay, hopefully you're back. All of these problems can be done by the charting method. So what is the half-life of a radioisotope that decays to 25% of its original parent in 100 years? Well, if we're going to set up that time, I'm going to do it up here. Time, half-life, time, parent, daughter. And by now, you probably can even drop doing the total. So 0, 0. This is a percentage one. So we start with 100%. Then we're going to have 50%. We're going to have 25%. 1, 2. That occurred in 100 years. 100 years divided by 2, because there's 2 half-lives there. That gave you 50 years. How much of a radioactive sample of cesium, a half-life of 30 years, is left after 200 years? So let's work this one at the bottom. We've got cesium, and it's got a half-life of 30 years. So I really don't have to do the counting, but we can do the time. Remember, this is the one for here. Time, parent. So we're going to start at 0. And it doesn't give me an amount, so let's say a percentage. We start at 100%. So we're going to go 30, 60, 90, 120, 150, 180. The next one here is going to be 210. That's 200 if you round it. So we had 100. This is going to be 50, 25, 12.5, 6.25, 3.125. I'm going to grab my calculator, make the math go much faster. 3.125, we're going to divide that by 2. This is going to be 1.5625. Divide that by 2. And that's going to be 0.78125. So how much is left? It's going to be between 1.56% and 0.78%. And you can answer a question just like that. Okay, let's look at this next one. A fossil contains less than 1% of its original carbon-14. When did the animal die if the half-life is 5,720 years? Okay. So this is a percent. We can use this same chart here, but our time is going to be different. So we know that our parent, we want to go to less than 1%. 1, 2, 3, 4, 5, 6, 7, 8 half-lives took me to less than 1%. So it's 7 to 8 half-lives. So we're going to take 8 times 5,720. So this animal died 45,000 years ago. So the charting method really does make things easier. I hope this video helped. If you have questions, go ahead and drop them in the comments. I'm going to try to start making question videos to post up because you guys ask great questions. Go ahead, follow, like Elements of Chemistry tutorials. As always, stay curious. Have a wonderful day and a good tomorrow. Stay safe out there.